Welcome to Dark Cosmos Theory. Before we dive into today's journey, make sure to hit that like button and subscribe if you haven't already. We've got an incredible exploration ahead, and I'd love to know where you're watching from. Drop your location in the comments below. Let's connect our global community of space enthusiasts. Now, picture this. At this very moment, you're careening through absolute darkness at velocities that would obliterate any known material. You're circling an invisible behemoth, caught in a spiraling dance you could never capture on film. Riding a stone so minuscule that humanity's entire existence could blink out of being tomorrow, and our galaxy wouldn't even register the loss. Today, we're going to traverse distances that fracture understanding, examine formations that eclipse imagination, and face down a reality that renders every human accomplishment barely more than a murmur in an endless expanse. By the time we finish this journey, you'll understand exactly how impossibly tiny you really are. Let's get started. A light year represents how far illumination travels across 12 months. Light outpaces everything else that exists in our universe. It bridges the gap between our planet and the nearest stellar body in slightly more than 8 minutes. Even moving at this unimaginable velocity, light requires a full year to span what astronomers label a light year. Here's what this distance means when converted to conventional measurements. Start with the figure 5.8. Now append 12 zeros behind it. That gives you approximately 5.8 trillion miles. Your automobile would need to maintain constant motion, never pausing for refueling, never stopping to rest, for upwards of 6 million years to traverse this span. No motor exists that could endure even a small percentage of such a voyage. Scientists utilize light years for measuring space because standard units become completely inadequate. Miles and kilometers transform into nonsense. Informing someone that an object sits 17 trillion miles distant conveys nothing meaningful to the human brain. The figure exceeds processing capacity. It carries zero intuitive weight. However, stating that something rests 3 light years away provides a conceptual framework. We can envision light, the speediest phenomenon we know, racing across darkness for 3 complete years before reaching its target. Our closest stellar neighbors sit more than 4 light years removed from us. The illumination you observe from those stars tonight departed their surfaces when you were 4 years younger than you are right now. Should that distant sun explode at this precise instant, you'd remain ignorant for 4 additional years. The separation functions as temporal transportation, revealing not what currently exists, but what previously existed. Every celestial body in our galaxy gets measured using these units. Our sun circles the galactic core at approximately 26,000 light-years distant. The galaxy itself extends 100,000 light-years from one rim to the opposite rim. These figures should induce existential dread. They should make you feel disconnected from all familiar reality. Because here's the critical part. A light year represents merely the smallest measurement we'll employ during this expedition. The structures we're preparing to examine are so colossal that even light years begin feeling insufficient. What you believe constitutes far is merely the starting point. You inhabit a particular location within the Milky Way. You're not randomly distributed, not aimlessly floating. You occupy a precise position that astronomers have charted and verified. That position is designated the Orion Arm, occasionally referenced as the Orion's Spur, a secondary spiral formation that links 2 more substantial structures. Our galaxy contains multiple primary spiral arms. The Perseus arm extends farther from the nucleus than our position does. The Sagittarius arm bends inward toward the core. We're situated in a diagonal connector between these massive features, a smaller element that astronomers disputed for many decades. Some labeled it merely a spur. Others maintained it qualified as a complete arm. Contemporary observations have resolved the disagreement. It's substantial enough to warrant recognition. You're not positioned at this arm's midpoint. You're not located at its boundary either. You sit nearer to the interior margin, the section that faces toward the galactic nucleus. This placement carries more significance than you might initially assume. Location dictates what becomes visible in your night sky. It dictates your level of safety. It dictates whether radiation from the core manages to reach your vicinity. The span from our current position to the galactic center has been calculated with improving accuracy over many decades. The presently confirmed approximation positions us approximately 26,000 light-years outward. Certain measurements indicate 27,000. The imprecision stems from the challenge of calculating distances across such tremendous spans while remaining trapped inside the very formation we're attempting to chart. Consider it analogous to attempting to calculate the dimensions of a forest while standing at its center. You can observe individual trees. You can move among them, but establishing where the forest terminates requires alternative methodologies. For our galaxy, astronomers employ stellar groupings, gas formations, and stellar movements to construct a chart. Each approach refines the representation. Our location is neither at the nucleus nor at the periphery. It's roughly equidistant between both extremes. If the galaxy resembled a vinyl record, we'd be positioned approximately midway between the center label and the outer rim. This halfway location means we're sufficiently removed from the core to circumvent its violent nature, yet close enough to gain from the abundant stellar population surrounding us. The orientation of our solar system doesn't correspond with the galactic orientation either. We're angled at roughly 60 degrees. It's comparable to sailing across the galaxy at an oblique angle. This tilt means that when you observe the band of the Milky Way extending across the evening sky, you're viewing the edge-on perspective of our galactic disk from a diagonal viewpoint. Relative to the galactic plane, we sit marginally above it by approximately 55 light-years. That's essentially nothing on galactic measurements. We're practically riding directly along the equator of the galaxy's disk. This nearness to the midplane maintains us embedded in the densest accumulation of stars and dust. However, there's something more peculiar about this location that rarely gets discussed. The Milky Way resembles a disk. Everybody recognizes this. But what they fail to mention is how astonishingly flat that disk actually proves to be. The galaxy spans 100,000 light-years in diameter, yet the disk, where most stellar bodies reside, measures merely 1,000 light-years in thickness at the spiral arms. Take a standard sheet of paper. The proportion of its width to its thickness approximates the galaxy's ratio. You're existing inside cosmic origami. This flatness isn't a gradual curve. It's an extreme compression of billions of suns into a slender plane. Why does this configuration form? Rotation provides the answer. The complete galaxy revolves. As it revolves, gravitational forces pull everything toward a shared plane, while angular momentum prevents absolute collapse. Stars, gas, and dust settle into the most slender possible arrangement that maintains structural stability. Think of it resembling pizza dough spinning airborne. Centrifugal forces flatten it thin. The central bulge at the galaxy's heart breaks this arrangement. There, stars cluster in a sphere roughly 10,000 light-years across. But beyond the bulge, the disk prevails. Most of the galaxy's visible matter concentrates in this paper-thin construction. Our position just 55 light-years above the galactic plane means we sit virtually exactly on the equator. Any closer, and we'd be immersed in the densest accumulation of interstellar dust. That dust obstructs visible light. It would hide our view of remote stars and render astronomy nearly impossible from our vantage point. The slender disk harbors the youngest stars, newborn from collapsing gas formations. The thicker disk, slightly more substantial at around 2,000 light-years in certain regions, contains older stars that have been expelled from the thin disk through gravitational encounters. But even this thick disk remains shockingly compressed relative to the galaxy's total width. If you could somehow position yourself outside the galaxy and examine it edge-on, you'd witness a glowing line stretching across space. The central bulge would manifest as a luminous protrusion in the middle. The disk would but taper to almost nothing at the margins. From that viewpoint, the Milky Way resembles more a cosmic razor blade than a majestic spiral. This flatness generates a peculiar optical phenomenon. When you observe the Milky Way band arcing across the night sky, you're witnessing the combined illumination of billions of stars compressed into that slender disk. You're looking through the disk from within it. The densest concentrations of stars extend along that band because that's where the plane intersects your field of vision. But this flatness also signifies something else, something most individuals don't comprehend. You're moving faster than any speeding projectile at this instant, far faster. You're moving faster than any rocket humanity has constructed. You simply cannot perceive it. The complete solar system, everything from our sun to the most distant icy bodies at the boundary, races around the galactic center at more than 500,000 miles per hour. That velocity is verified through decades of astronomical calculations. Scientists monitor stellar motion, measure the Doppler displacement in their light, and compute orbital velocities. The figures are indisputable. We're careening through space at velocities that would vaporize any spacecraft we could construct. Why don't you sense it? Same explanation you don't sense Earth's rotation. You're moving alongside it. Everything surrounding you shares identical velocity. The atmosphere, the surface, the structures, the clouds overhead, all of it moves together in a coordinated rush around the galactic core. There's zero wind resistance in space, zero friction, zero sensation of movement. But here's where things become strange. Despite moving at over 500,000 miles hourly, completing one orbit still requires an incomprehensibly extended duration. The distance encircling the galactic center is so vast that speed becomes almost irrelevant. It's comparable to attempting to sprint around Earth's equator. Even if you could maintain highway speeds, the sheer distance would require forever to cross. Stars nearer to the galactic center move faster than we do. Stars positioned farther outward move slower. This creates a spiral configuration that rotates like a pinwheel. But individual stars don't preserve their positions in the spiral arms. The arms themselves aren't fixed stellar structures. They're density waves, regions where stars temporarily congregate as they pass through, like automobiles bunching up in traffic. The speed we're moving at gets determined by the mass inside our orbit. All the stars, gas, dust, and mysterious dark matter between us and the center contribute gravitational pull. That pull accelerates us. It prevents us from flying off into intergalactic space. It's a delicate equilibrium between inward gravity and outward momentum. If we moved slower, we'd spiral inward toward the core. If we moved faster, we'd escape the galaxy entirely. Our current speed represents an Aston's equilibrium, a cosmic balance that's been maintained for billions of years. The solar system has completed roughly 20 orbits since it formed. 20 laps around a track so immense that each lap requires eons. Other galaxies move even faster. The Andromeda galaxy rushes toward us at more than 200,000 miles per hour. When it arrives, the collision will reshape both galaxies into something unprecedented, but that remains billions of years distant. Right now, you're focused on a more immediate question. How extended does one orbit require? The previous time Earth occupied this exact position in the galaxy, dinosaurs dominated the planet. Mammals existed, but only as diminutive creatures concealing in the shadows. The continents sat in different positions. The climate bore zero resemblance to today. None of the species you recognize had evolved yet. This period is designated a galactic year. It's the duration required for our star and its planets to complete one full orbit around the clash. Milky Way's center. The confirmed duration is roughly 250 million Earth years. Some approximations suggest 200 million, others extend it to 230 million. The variation derives from uncertainties in measuring both our orbital speed and the exact distance we traverse. Contemplate what this signifies. Since Earth formed roughly 4.5 billion years ago, the planet has completed merely about 18 orbits, 18 trips around the galaxy. Human civilization has existed for perhaps 10,000 years. That's less than 1/25,000th of a single galactic year. Blink, and you'd miss it entirely. The previous galactic year witnessed the rise and fall of complete ecosystems. The Triassic period commenced. Dinosaurs emerged and diversified. The supercontinent Pangaea started fragmenting. Massive volcanic eruptions reshaped the planet. The Permian extinction, the most catastrophic mass extinction in Earth's history, occurred. More than 90% of marine species vanished. Life approached closer to complete annihilation than at any other moment. By the time we complete the current galactic year, the continents will have drifted into unrecognizable configurations. New mountain ranges will have risen. Old ones will have eroded to nothing. Species that exist today will be extinct. New forms of life will have evolved. The climate will have shifted multiple times. Ice ages will come and go. Human civilization, if it survives, will be unrecognizable. The totality of recorded history, from the first cities to space exploration, represents less than 1/40,000th of a galactic year. You could fit 40,000 human civilizations, each lasting as long as ours, into a single orbit. The orbital period isn't perfectly regular either. Gravitational interactions with other stars, passage through the spiral arms, and encounters with massive gas clouds all introduce tiny variations in our speed. Sometimes we move marginally faster, sometimes marginally slower. Over millions of years, these variations average out, but they're genuine. During the previous galactic year, our star passed through the spiral arms multiple times. Each passage increased the density of nearby stars and triggered bursts of star formation in surrounding gas clouds. Some scientists theorize that these passages could correlate with mass extinctions on Earth, though this remains controversial and unconfirmed. What will Earth resemble when we return here again? Nobody knows. Nobody can predict that far into the future. But one thing is certain: 26,000 light years. You read those words, and your brain processes them as information. But you don't truly comprehend what they signify. You cannot. The human mind didn't evolve to grasp distances measured in trillions of miles. Let me attempt to help you understand. Take a commercial jet, the kind that transports you on vacation. That jet cruises at approximately 500 miles per hour. Now imagine directing that jet toward the galactic center and maintaining the engines running continuously, never landing, never refueling, just flying in a straight line through empty space at cruising speed. How extended would it require to reach the center? Roughly 6 million years. The jet would need to fly continuously from before modern humans evolved all the way to today, and it would only be partway there. The complete span of human existence from our earliest ancestors to the present wouldn't cover even a fraction of the journey. Light makes the identical trip in 26,000 years. But light moves at 670 million miles per hour. Nothing can move faster. Light represents the ultimate speed limit of the universe. And even light racing through the void without rest takes 26 millennia to reach the galaxy's heart. This signifies something profound. When you look toward the constellation Sagittarius, where the galactic center resides, you're not witnessing what exists there now. You're witnessing what existed there 26,000 years ago, before agriculture, before writing, before civilization. The light reaching your eyes tonight departed the galactic core when humans were still hunter-gatherers painting on cave walls. If the galactic core exploded right now, we wouldn't know for 26,000 years. The explosion could have already happened. We'd have zero warning, zero indication. The light from that catastrophe is still racing toward us through the darkness, and it won't arrive for millennia beyond count. Distance and time become identical at this scale. Astronomy is time travel. Every distant object you observe reveals its past. The farther you look, the farther back you witness. The galactic center exists in your past, permanently delayed by the speed limit of light. Radio signals travel at light speed as well. If aliens at the galactic core attempted to contact us today using radio waves, their message would require 26,000 years to arrive. By the time we received it and transmitted a reply, another 26,000 years would elapse before they heard our response. A simple conversation would require over 50,000 years. The distance also affects what we can observe. Dust clouds obstruct visible light. The galactic core is concealed behind vast sheets of interstellar material. We can only observe it using infrared light, radio waves, and X-rays, which penetrate dust more easily. Without invisible light, the center remains invisible, shrouded in darkness. But the distance protects us as well. 26,000 light-years is sufficiently far to shield us from the violence at the core, the radiation, the gravitational chaos, the supermassive black hole consuming everything nearby. We orbit safely in the suburbs while the center rages. Yet even this enormous distance is minuscule compared to what follows. Scale models help us comprehend the incomprehensible, so let's shrink the galaxy. Imagine the entire Milky Way compressed down until it fits perfectly over North America. The galactic disk extends from the Atlantic to the Pacific, from Canada to Mexico. 100,000 light-years compressed into approximately 3,000 miles. On this scale, our entire solar system, from our star out to the orbit of Neptune, shrinks to the dimensions of a single blood cell. Not a basketball, not a marble, a microscopic cell invisible to the naked eye. You could fit millions of solar systems across a single inch. Earth itself becomes smaller than an atom. You couldn't observe it with any microscope. It would exist only as a theoretical point, a mathematical abstraction too diminutive for physical reality to represent. Everything you know, everyone who ever lived, all of human history, compressed into less than atomic dimensions. The distance between our star and the nearest neighboring star, approximately 4 light-years, becomes roughly 1 inch on this scale. 1 inch of empty space between one blood cell and the next. Stars are astonishingly far apart relative to their size. The galaxy is mostly emptiness, punctuated by tiny points of light separated by cosmic voids. Our position in the Orion Arm, we'd sit somewhere over Kansas. The galactic center would rest near Washington, D.C. on the east coast. The edge of the galaxy would reach Los Angeles on the west coast. The supermassive black hole at the core, which we'll explore later, would be smaller than a grain of sand sitting in the nation's capital. But here's what shatters your intuition. On this scale, the galaxy's thickness, that 1,000 light-year thin disk, would measure only 30 miles. Picture North America compressed down to a sheet of glass 30 miles thick. That's the structure we inhabit, a continent-sized window pane floating through space. The spiral arms would appear as marginally denser regions of blood cells, zones where the concentration increases, but individual cells remain separated by vast emptiness. The arms don't touch. They're not solid. They're simply probability waves, regions where stars cluster marginally closer together than average. Other galaxies exist on this scale as well. Andromeda, our nearest large neighbor, would sit roughly 250,000 miles distant, approximately the distance from Earth to our actual natural satellite. Andromeda is close, dangerously close. It's already approaching, and collision is inevitable. The local group of galaxies, which includes the Milky Way, Andromeda, and several dozen smaller galaxies, would fit inside a sphere approximately 3 million miles across. All the galaxies we consider neighbors, all the stellar systems we interact with gravitationally, contained in a region less than the distance between Earth and our actual star. This scale model breaks down when you attempt to include the entire universe. Even compressed to this degree, the observable universe would still extend trillions of miles in every direction. The scale required to visualize everything is too extreme. The numbers stop making sense. But right now, focus on that blood cell hovering over Kansas. That's your home. That's everything you know. And we haven't even discussed the details yet. Count to 10. It requires roughly 10 seconds. Count to 100, maybe 2 minutes. Now attempt counting to 1 billion. Don't actually attempt it. You'd need 32 years if you counted one number per second without sleeping. You'd expire of old age before finishing. The Milky Way contains between 100 billion and 400 billion stars. The exact number remains uncertain because faint stars are nearly impossible to detect at great distances. But even the conservative estimate of 100 billion should shatter your sense of significance. 100 billion stars signifies 100 billion stellar systems. Most stars possess planets. Recent observations confirm that planetary systems are the standard, not the exception. This suggests at least 100 billion planets exist in our galaxy alone. Many of those planets orbit in habitable zones where liquid water could exist. Earth is one planet among 100 billion. Our star is one among 100 billion. You are one organism among billions on one planet among billions, orbiting one star among billions. The layers of insignificance accumulate until meaning dissolves. But let's make this more visceral. Imagine every star in the galaxy is a grain of sand. You'd need enough sand to fill several Olympic swimming pools. Now imagine attempting to locate one specific grain of sand in those pools. That's the challenge of locating our star from outside the galaxy. We'd be indistinguishable from the background, lost in the crowd. The stars aren't evenly distributed either. The central bulge contains the highest density. Billions of stars pack into a relatively small volume, far more crowded than our suburban neighborhood. Out in the spiral arms, stars spread thinner. The spaces between them widen. But even in the sparse regions, you'd still find millions of stars within a sphere just a few hundred light years across. Different types of stars populate different regions. The disk contains young, hot stars burning blue and white. These stars formed recently from gas clouds and haven't had time to age. The central bulge glows yellow and red with ancient stars billions of years old. These stars formed when the galaxy was young, when the universe contained fewer heavy elements. Some stars move faster than others. High-velocity stars kicked out of their original orbits by gravitational encounters zip through the galaxy at extreme speeds relative to their neighbors. Hypervelocity stars move so rapidly they'll eventually escape the galaxy entirely, flung out into intergalactic space by close encounters with the supermassive black hole at the core. Binary star systems are common. More than half of all stars possess at least one companion. Some stars orbit in triple or quadruple systems, complex gravitational dances that make stable, planetary orbits nearly impossible. A few stars exist in clusters containing thousands of siblings, all born from the same gas cloud, but most stars are dim. Red dwarfs, the smallest and faintest stars, outnumber all other types combined. They burn so slowly they'll outlive the universe's current age. Stars like ours, yellow dwarfs, represent a minority. Massive blue giants, the brightest stars, are the rarest of all and burn out quickly. And among all these stars, all these worlds, all this vastness, how many civilizations might exist? How many are looking up at their sky right now asking the identical question we are? You've witnessed images of the Milky Way, beautiful spiral arms curling outward from a brilliant core, photographed from an impossible angle. But those images are artists' renderings, educated guesses, informed approximations. Nobody has photographed our galaxy from outside because getting outside is impossible. We exist inside the structure we're attempting to chart. It's comparable to being trapped inside a house and attempting to describe what the house resembles from the street. You can measure room dimensions. You can count the floors, but you cannot observe the exterior. You cannot verify the roof's configuration or determine the color of the siding. For most of human history, we didn't even know we inhabited a galaxy. The Milky Way band extending across the night sky was mysterious. Some cultures thought it was milk spilled by deities. Others called it a river of light. The ancient Greeks provided it the designation we still use, but nobody understood what they were witnessing. Only in the early 20th century did astronomers confirm that the Milky Way is a galaxy, one among billions. Edwin Hubble proved that other galaxies exist beyond our own. Suddenly, our entire cosmic neighborhood was recontextualized. We weren't observing the edge of the universe. We were observing the edge of our own island, one structure among countless others. Mapping the spiral arms required decades of painstaking work. Astronomers used radio telescopes to detect neutral hydrogen gas clouds, gas concentrates in spiral arms, marking their locations. By measuring the distances to these clouds and tracking their motions, scientists slowly reconstructed the galaxy's structure. The work continues. Recent observations suggest the Milky Way possesses four major spiral arms, not two as once thought. The Scutum Centaurus arm and the Perseus arm are well established. The Sagittarius arm and the Norma arm complete the quartet, but details remain fuzzy. The exact number of minor arms and spurs continues to be debated. Our location in the Orion spur makes mapping even harder. We sit inside a minor feature surrounded by dust and gas that obstructs our view in multiple directions. Looking toward the galactic center, we observe only a few thousand light years before interstellar dust absorbs all visible light. The core remains concealed unless we switch to infrared or radio wavelengths. Looking outward toward the galaxy's edge presents different challenges. Fewer stars exist in that direction, distances become harder to measure. The edge of the disk isn't sharp. It fades gradually into the halo, making it impossible to define precisely where the galaxy terminates. If we could somehow launch a spacecraft fast enough to escape the galaxy and photograph it from a distance, the journey would require millions of years. Even traveling at light speed, leaving the galaxy and reaching a vantage point sufficiently far away to observe the full structure, would require a 100,000-year journey. By the time the spacecraft transmitted back images, human civilization might no longer exist. So we're stuck guessing, building models, comparing our galaxy to others we can observe, assuming that what we observe in distant spirals applies to our own. It's frustrating, it's limiting, but it's the only method available. And there's something else we cannot observe, something far more massive than all the stars combined. At the center of the Milky Way sits a black hole so massive it defies intuition. Its designation is Sagittarius A star, often written as an abbreviation. The mass of this object equals roughly 4 million times the mass of our star, 4 million stellar masses compressed into a region smaller than the orbit of Mercury. This is confirmed, not theoretical, not hypothetical. Astronomers have tracked individual stars orbiting this black hole for decades. They've measured orbital periods, speeds, and distances. The mathematics is undeniable. Only a black hole could produce the gravitational effects observed. The black hole's event horizon, the point of no return where escape becomes impossible, possesses a radius of roughly 7 million miles. That's minuscule by galactic standards. You could fit this black hole inside the distance between our star and the planet Mercury. Yet its gravitational influence extends across thousands of light years. Scientists captured the first image of this black hole in 2022 using the Event Horizon Telescope, a network of radio observatories spread across Earth. The image displays a bright ring of superheated gas surrounding a dark shadow. The shadow is the black hole itself, a region so gravitationally intense that not even light can escape. The bright ring is material falling inward, accelerated to near light speed and heated to billions of degrees. The black hole is mostly dormant now. It consumes relatively little material compared to supermassive black holes in other galaxies, but evidence suggests it wasn't always quiet. Approximately 200 years ago, the black hole experienced a major outburst, consuming a large amount of gas and radiation that we're only now detecting as it reflects off nearby clouds. What triggered that feeding frenzy remains unknown. Stars orbit this monster on frighteningly tight paths. One star, designated by astronomers with a simple letter and number combination, completes an orbit in just 16 years. 16 years to circle a black hole at distances closer than Pluto orbits our star. The speed required for such an orbit approaches 3% of light speed. The star experiences relativistic effects, time dilation, and gravitational redshift as it whips around the black hole. During close approach, the star passes within just 17 light hours of the event horizon. At that distance, tidal forces nearly tear the star apart. The difference in gravitational pull between the star's near side and far side is immense. Only the star's internal structure and orbital speed prevent complete destruction. Watching these stars orbit has allowed scientists to test Einstein's general relativity in extreme conditions. Predictions about orbital precession, gravitational time dilation, and light bending all match observed reality. General relativity remains undefeated, but we're pushing it to its limits. Thousands of smaller black holes orbit the supermassive one. These stellar mass black holes, the remnants of massive stars, the cluster near the galactic core, where star density peaks. They form a dangerous neighborhood, a region where gravitational interactions are common and violent. Gas clouds occasionally wander too close to the central black hole. Astronomers watch them get torn apart by tidal forces, stretched into long filaments before vanishing across the event horizon. One cloud passed close enough a few years ago that scientists predicted its complete destruction. It survived. How? Mystery. What happens to matter that crosses the event horizon? Unknown. General relativity predicts a singularity, a point of infinite density where physics breaks down. But quantum mechanics suggests something else might occur. Nobody knows. Nobody can observe what happens inside. And this black hole is considered small. Some galaxies harbor black holes billions of times our star's mass. But for us, this is the monster we orbit. This is the anchor holding our galaxy together. There are stars near the galactic center that move so rapidly they seem impossible. Stars racing around the supermassive black hole at speeds that make our orbital velocity look glacial. One star completes its entire orbit in 16 years, 16 Earth years from start to finish. Our star requires 250 million years to orbit once. This star accomplishes it in 16. The speed difference is incomprehensible. The star reaches roughly 3% of light speed at its closest approach to the black hole. That's nearly 6 million miles per hour. Nothing in our solar system comes remotely close to these velocities. Astronomers have tracked this star since the 1990 seconds. They've watched it complete multiple orbits. Its path is highly elliptical. At its farthest point, it ventures out relatively far from the black hole. At its closest approach, called perinigricon in astronomical terminology, it dives within 17 light hours of the event horizon. What does 17 light hours signify? It's the distance light travels in 17 hours, roughly 11 billion miles. That sounds far until you remember the black hole's event horizon is only 7 million miles across. The star passes just a few hundred times the black hole's radius. In cosmic terms, that's skimming the surface. At closest approach, the star experiences gravitational forces that warp spacetime itself. Time passes slower for the star than for distant observers. This is confirmed time dilation, a prediction of general relativity. If you could somehow stand on that star during perinigricon, you'd age marginally slower than people far from the black hole. The effect is tiny but measurable. The star's light also experiences gravitational redshift. As photons climb out of the deep gravitational well, they lose energy and shift toward longer, redder wavelengths. Astronomers measure this shift and use it to confirm the black hole's mass. Every observation adds more precision to our understanding. Tidal forces at perinigricon should tear the star apart. The gravitational pull on the star's near side is significantly stronger than the pull on its far side. This difference, the tidal force, stretches the star, yet it survives. Its internal structure and rapid orbital motion save it from destruction. multiple stars orbit at similar distances. Scientists have catalogued dozens of these high-velocity objects, each designated with simple alphanumeric codes. They're called stars, and they represent a unique laboratory for testing extreme physics. No other location in the galaxy offers such extreme conditions at accessible observation distances. Some of these stars are so close to the black hole that their orbits precess measurably. Precession signifies the orbit itself rotates over time, like a spirograph. General relativity predicts this effect near massive objects. Observations match predictions perfectly. Einstein was right again. How did stars get into such dangerous orbits? Two theories dominate. Either they formed farther out and were gravitationally kicked inward through interactions with other stars, or they formed in a disk of gas around the black hole itself. Both scenarios are plausible. Neither is confirmed. What's certain is that these stars won't survive forever. Eventually, gravitational interactions will either fling them out of the galactic core or send them plunging across the event horizon. Their current orbits are temporary, cosmically speaking, but for now, they provide our best view of black hole physics, and their existence proves something else. The galactic core is far more dangerous than our safe suburban orbit. We orbit 26,000 light-years from the galactic center. This distance isn't random, it's not accidental. Our location in what astronomers call the galactic suburbs offers unique advantages that make complex life possible. Move significantly closer or farther out, and conditions change dramatically. The galactic core is violent, star density peaks there. Stars pass close enough to disturb each other's planetary systems gravitationally. Planets get ejected into interstellar space. Stellar collisions, though rare, occur more frequently than anywhere else in the galaxy. Close binary stars merge. Black holes consume gas clouds and occasional stars. Radiation at the core is intense. The supermassive black hole emits X-rays and gamma rays. Supernovae, the explosive deaths of massive stars, happen more often in regions of high star density. Each supernova releases radiation that sterilizes nearby planets. The background radiation level near the core is thousands of times higher than in our neighborhood. If Earth orbited a star near the galactic center, life as we know it couldn't exist. The radiation would break down complex molecules. Atmospheric chemistry would be disrupted. Mutations would occur too rapidly for evolution to stabilize. Any biosphere would be repeatedly reset by nearby stellar violence. Moving too far outward presents different problems. The outer edge of the galaxy contains fewer stars. Heavy elements, the building blocks of planets and life, are scarcer. Stars in the outer regions formed from gas clouds with lower metallicity. Astronomers speak for elements heavier than hydrogen and helium. Rocky planets like Earth might not form at all in those regions. Our distance from the center places us in the galactic habitable zone, a theoretical region where conditions favor complex life. We're sufficiently far from the core to avoid its radiation and gravitational chaos, yet close enough to benefit from the chemical enrichment produced by generations of stars. This is the sweet spot. The spiral arm structure matters as well. We sit inside the Orion spur, a minor arm between two major ones. This location means we don't spend much time crossing through the denser regions of major spiral arms, where supernova rates increase. We avoid the most dangerous neighborhoods while still residing in a region rich with stars. Our star's orbit is nearly circular, another rare advantage. Many stars follow highly elliptical paths that carry them through spiral arms regularly. Our stable circular orbit keeps conditions relatively constant. We don't experience extreme variations in stellar density or radiation exposure as we circle the galaxy. The local bubble, a region of low-density space carved out by ancient supernovae, surrounds our solar system. This bubble extends hundreds of light-years in all directions. It's a protective cocoon, a region where interstellar gas and dust are thinner than average. This thinness reduces the friction our star experiences as it moves through space. Everything about our location suggests remarkable luck. We orbit in a relatively safe zone. We avoid the core's violence. We benefit from chemical enrichment. Our orbit is stable and circular. The local bubble protects us. Stack up all these factors and you realize how rare our situation might be. How many other stars enjoy similar advantages? Unknown, but the percentage is likely small. Most stars orbit in less favorable conditions. They experience higher radiation, greater gravitational disturbance, or insufficient heavy elements for planet formation. And yet, despite our privileged location, we're still just one star among billions. Our neighborhood might be safe, but it's not special. We're suburbanites in a city of stars, comfortable but unremarkable. Which brings us to the structure we inhabit. The galaxy is mostly empty space. Between stars, vast voids stretch for light years. But the stars themselves, along with their gas and dust, concentrate in specific regions. The primary region is the thin disk, and it's far thinner than most people imagine. 1,000 light years thick at the spiral arms. That's the disk's vertical dimension. Compare this to the galaxy's diameter of 100,000 light years. The ratio is 1 to 100. Imagine a dinner plate as wide as a football field. That's the galaxy's proportions, a cosmic pancake so flat it challenges comprehension. This flatness arises from rotation. When the galaxy formed billions of years ago, gas and dust swirled around the developing center. Gravity pulled material inward. Angular momentum, the tendency of spinning things to keep spinning, prevented complete collapse. The result is a rotating disk, the most stable configuration for a spinning system. Within this disk, stars orbit the galactic center on roughly circular paths. Each star maintains a nearly constant distance from the core, like cars on a circular racetrack. But unlike cars, stars don't travel in packs. Each follows its own independent orbit. Sometimes orbits cross. Stars pass near each other, exchange gravitational energy, and drift to new orbits. The thin disk contains the youngest stars. Hot blue giants, blazing white stars, and yellow stars like ours populate this region. These stars formed relatively recently from gas clouds within the disk itself. Star formation continues today wherever gas clouds collapse under their own gravity. Gas and dust also concentrate in the thin disk. Vast molecular clouds, nurseries where new stars are born, float through the galactic plane. These clouds are cold and dense. When they collapse, they fragment into clumps that ignite as new stars. The process has continued for billions of years and will continue for billions more. The disk isn't perfectly smooth. Density variations create the spiral arms. Gas clouds pile up in certain regions, triggering bursts of star formation. These regions glow brightly because massive young stars shine intensely but briefly. The spiral arms appear bright primarily because of these young stars, not because they contain fundamentally more stars overall. Above and below the thin disk lies the thick disk, a puffier region containing older stars. These stars were born in the thin disk but got kicked out vertically by gravitational interactions. They orbit on paths tilted relative to the galactic plane, creating a halo of stars above and below the main structure. The thick disk is roughly twice as thick as the thin disk, but contains fewer stars overall. Its stars are older and redder. They formed when the galaxy was younger and have been wandering ever since. Some orbit at angles so steep they barely pass through the thin disk at all. Our position within the thin disk, just 55 light years above the midplane, means we're embedded in the densest stellar population. When you look at the Milky Way band across the night sky, you're observing this disk edge on. The combined light of billions of stars compressed into that thin structure creates the glowing band, but the disk only accounts for a fraction of the galaxy's mass. Most of the mass exists in a completely different form, a form we cannot observe. 90% of the galaxy's mass is invisible, completely invisible. It emits zero light, It reflects zero light. It absorbs zero light. We know it exists only through its gravitational effects. This mysterious substance is designated dark matter, and it dominates the Milky Way. Here's how we discovered it. Astronomers measured the rotation speeds of stars at different distances from the galactic center. They expected outer stars to orbit more slowly than inner stars, following the identical physics that governs planets in our solar system. Neptune orbits slower than Earth because it's farther from the gravitational source. But the galaxy doesn't function that way. Stars near the edge orbit almost as rapidly as stars closer to the center. The rotation curve stays flat instead of declining. This should be impossible. The visible matter in the galaxy cannot produce enough gravity to keep outer stars moving so rapidly. They should fly off into space. Three explanations exist. Either our understanding of gravity is wrong, the galaxy contains far more mass than we can observe, or something else we haven't discovered is happening. Most astronomers favor the second option. There must be additional mass distributed in a roughly spherical halo around the visible galaxy. This invisible mass is dark matter. How much dark matter exists? Current estimates suggest the dark matter halo contains roughly 10 times the mass of all visible stars combined. The halo extends far beyond the visible disk, possibly stretching hundreds of thousands of light years from the galactic center. We orbit inside this halo. We're surrounded by invisible mass we cannot detect directly. What is dark matter composed of? Unknown. Decades of experiments have failed to detect dark matter particles directly. We know it's not ordinary matter like protons and neutrons. It doesn't interact with light at all. It passes through normal matter, without collision, like ghosts passing through walls. Dozens of theories attempt to explain dark matter. Some propose exotic particles created in the early universe. Others suggest modifications to gravity itself. A few radical ideas even question whether dark matter exists at all, proposing instead that our observations are misinterpreted. But the gravitational evidence is overwhelming. Something is there. The Milky Way's dark matter halo acts like invisible scaffolding. It holds the galaxy together. It prevents outer stars from escaping. It anchored the galaxy's formation billions of years ago when gas collapsed to form the first stars. Without dark matter, galaxies as we know them couldn't exist. Other galaxies also possess dark matter halos. Small dwarf galaxies appear to be dominated by dark matter, containing almost nothing else. Massive galaxy clusters hold enough dark matter to bend light from background galaxies gravitationally, creating distorted images visible through telescopes. The presence of dark matter affects everything in the galaxy: star orbits, gas cloud movements, the formation of spiral arms, even the motions of satellite galaxies orbiting the Milky Way. Dark matter's gravity influences structures across all scales. Despite years of searching, dark matter remains elusive. Particle detectors buried deep underground wait for collisions that never come. Space telescopes look for annihilation signatures. Colliders smash particles together, hoping to create dark matter in the debris. So far, nothing. We inhabit a galaxy whose mass is mostly mystery. The stars, planets, gas, and dust we can observe represent only 10% of the total. The rest is invisible, undetectable, and entirely unknown. It's a humbling reminder of how little we truly understand. The Orion spur sits between two much larger structures. These are the major spiral arms that dominate our region of the galaxy. To our galactic north lies the Perseus arm. To our south curves the Sagittarius arm. Both dwarf our modest neighborhood in size and stellar population. The Perseus arm stretches thousands of light years in length and hundreds of light years in width. It's one of the galaxy's two primary spiral arms, containing billions of stars, countless gas clouds, and active star formation regions. When you observe images of distant spiral galaxies, the bright arms you witness are structures like Perseus, dominant features that define the galaxy's appearance. This arm sits roughly 6,000 500 light-years farther from the galactic center than we do. That might sound like a safe distance, until you remember that galactic structures don't possess sharp boundaries. The outer edge of the Perseus arm approaches our position. We're close enough to observe stars within it, close enough to feel its gravitational influence subtly. Star formation in the Perseus arm outpaces formation in the Orion spur. Massive molecular clouds collapse more frequently there. Young star clusters blaze with blue and white light. These regions are violent nurseries where stellar birth and death happen on accelerated timescales. Supernovae detonate regularly, seeding the arm with heavy elements. The Sagittarius arm curves inward toward the galactic core. It sits closer to the center than we do, wrapping around the galaxy's heart like a spiral staircase. This arm contains similar stellar populations to Perseus, but occupies a more dangerous neighborhood. Proximity to the core signifies higher radiation levels, more frequent stellar interactions, and greater gravitational complexity. Between these two giants, the Orion spur looks almost accidental. Some astronomers questioned whether it qualified as a true arm or was merely a bridge connecting Perseus and Sagittarius. Recent measurements suggest it's substantial enough to merit arm status, but it remains the smaller sibling in this family. The spiral arms aren't solid structures. Stars don't stay locked in fixed positions within them. Instead, the arms are density waves, regions where stars temporarily cluster as they orbit. Think of it like traffic on a circular highway. Cars bunch up in certain sections, creating apparent structures that move around the loop even though individual cars pass through. This signifies stars drift in and out of spiral arms over millions of years. Our star has passed through spiral arms multiple times during its lifetime. Each passage increased the local stellar density temporarily, exposing us to more nearby stars and marginally higher supernova risk. But these passages are brief on galactic timescales. The gravitational influence of spiral arms affects more than just stellar orbits. Gas clouds get compressed as they enter the arms, triggering star formation. This is why arms appear bright in photographs. They're not denser in total mass by huge margins, but they contain more young, luminous stars that dominate visible light. As our solar system orbits, we're currently moving toward the Perseus arm. Millions of years from now, we'll pass through its outer regions. The stellar density around us will increase marginally. More nearby stars will become visible. The risk of supernova exposure will rise temporarily. Then we'll emerge on the far side and drift toward the outer galaxy. This cycle has repeated throughout Earth's history. Our planet has witnessed many different stellar neighborhoods. The night sky looked different in the past and will look different in the future. Constellations change. Nearby stars come and go. The only constant is motion. Living between major arms offers protection. We avoid the densest regions where stellar violence peaks, but we're close enough to benefit from chemical enrichment. It's another example of our fortunate location. But location is only part of the story. Understanding the full structure requires examining the galaxy from outside. Imagine you could depart the galaxy, board a faster-than-light spacecraft, and travel outward at impossible speeds. As you climb away from the galactic plane, the disk begins to reveal itself. First, you observe your local neighborhood from above. Then, wider regions come into view. Eventually, the entire structure spreads beneath you like a cosmic pinwheel. From this impossible vantage point, the Milky Way looks flatter than you imagined. The disk appears almost two-dimensional, a thin sheet of light extending in all directions. The central bulge interrupts the flatness, glowing yellow and orange with ancient starlight. But beyond the bulge, the disk dominates. 4 spiral arms curl outward from the center. 2 major arms, Perseus and Scutum Centaurus, define the structure. 2 smaller arms, Sagittarius and Norma, fill the gaps. The Orion spur, where Earth resides, appears as a minor diagonal bridge, barely visible compared to the major features. You'd need to zoom in considerably to pick out our location. The arms don't touch, gaps exist, Between them, regions of lower stellar density where stars spread thinner. These interarm regions are dimmer, harder to observe, but they still contain billions of stars. The arms stand out primarily because of young, massive stars that burn intensely but briefly. Colors vary across the disk. The core glows red and yellow, dominated by ancient stars billions of years old. The spiral arms blaze blue and white, where young stars formed recently. Between the arms, colors shift toward yellow and orange, indicating intermediate age stellar populations. The galaxy is a rainbow of stellar evolution, each color telling a different story. Dust lanes trace the spiral arms' inner edges. These dark regions obstruct visible light, creating intricate patterns of shadow and illumination. The dust isn't uniformly distributed. It clumps into clouds and filaments, obscuring background stars and creating stunning contrasts between light and dark. The disk isn't perfectly flat, even from this perspective. Warps and ripples disturb the plane, likely caused by gravitational interactions with satellite galaxies orbiting the Milky Way. The outer disk bends marginally upward on one side, downward on the other. It's like a vinyl record left in the heat, deformed but still functional. Beyond the visible disk, the dark matter halo extends invisibly outward. You cannot observe it, but its gravitational influence shapes everything. The halo is roughly spherical, encompassing the disk and bulge like an enormous bubble. Its outer boundary remains undefined, fading gradually into intergalactic space. Satellite galaxies orbit in the halo. Small dwarf galaxies containing millions or billions of stars each circle the Milky Way like moons around a planet. The two largest, visible from Earth's southern hemisphere, are the Magellanic Clouds. They orbit roughly 160,000 light-years from the galactic center, well outside the visible disk. The Milky Way is consuming some of these satellites. The closest dwarf galaxy is being torn apart by tidal forces. Its stars stripped away and absorbed into the galactic halo. This process has happened many times throughout the galaxy's history. Small galaxies merge into larger ones, contributing their stars and gas to the growing structure. From even farther away, the Milky Way begins to look small. Other galaxies appear in the distance. Andromeda, roughly 2.5 million light-years away, dominates the view. It's nearly twice the Milky Way's size, a massive spiral heading toward inevitable collision. Smaller galaxies dot the space between them, members of the local group bound together gravitationally. Pull back further and the Milky Way becomes just one galaxy among thousands in the local supercluster. Individual features vanish. The spiral arms disappear. Even the galactic bulge shrinks to insignificance. What seemed enormous from inside becomes a tiny smudge of light among countless others. At the galaxy's heart, before you reach the supermassive black hole, sits a vast sphere of ancient stars. This is the central bulge, and it represents the galaxy's oldest component. 10,000 light-years in diameter, this structure formed when the universe was young and has persisted ever since. The bulge glows yellow and orange. These colors indicate old stellar populations. Red giants dominate the bulge, massive stars in their final evolutionary stages that have swollen to enormous sizes. Yellow stars like ours exist here as well, but aged billions of years. Blue stars, the young hot ones that populate spiral arms, are almost entirely absent. Why the age difference? Star formation in the bulge ended long ago. The gas and dust required for making new stars were either consumed in ancient stellar births or expelled by stellar winds and supernovae. What remains is a population of ancient survivors, stars that formed when the galaxy first assembled. The bulge contains roughly 20 billion stars. That's a small fraction of the galaxy's total population, but packed into a relatively tiny volume. Stellar density in the bulge exceeds density in the disk by factors of hundreds or thousands. Stars crowd together more tightly than anywhere else in the galaxy except the immediate vicinity of the central black hole. If Earth orbited a star in the bulge, the night sky would look completely different. Instead of a few thousand visible stars, millions would be bright enough to observe with naked eyes. The sky would never be truly dark. Even at midnight, the combined light of nearby stars would create a permanent twilight. Reading by starlight would be trivial, but conditions in the bulge are hostile to life as we know it. The stellar density increases collision risks. Planetary systems get disrupted by passing stars more frequently. Gravitational interactions eject planets from their orbits or send them plunging into their parent stars. Stable conditions, the kind required for billions of years of biological evolution, are rare. Radiation levels are higher as well. More stars signify more supernovae. More supernovae signify more high-energy particles flooding the interstellar medium. Any planet's atmosphere would face constant bombardment from cosmic rays. Mutation rates would soar. Complex life might struggle to evolve or survive. The bulge isn't perfectly spherical. It's bar-shaped, elongated along one axis. This bar structure is common in spiral galaxies. Roughly 2/3 of all spirals display central bars. The bar rotates as a unit, its stars locked into resonant orbits that maintain the shape over billions of years. The bar's exact dimensions remain debated. Estimates range from 3,000 to 16,000 light-years in length. Measuring the bar's size is difficult because we view it from inside the disk, not from a clear external perspective. Different measurement techniques yield different results. This bar plays a crucial role in galactic dynamics. It funnels gas inward toward the central black hole, feeding the monster at the core. It also affects stellar orbits throughout the inner galaxy, creating resonance patterns that influence spiral arm structure. The bar isn't static. It evolves slowly over hundreds of millions of years. Astronomers initially didn't realize the Milky Way possessed a central bar. The discovery came gradually as infrared telescopes pierced the dust, obscuring our view of the core. Infrared light passes through dust more easily than visible light. Once astronomers could observe the bulge clearly, the bar structure became obvious. The bulge also contains globular clusters, ancient stellar cities orbiting in the galactic halo. These clusters are some of the oldest objects in the universe, formed shortly after the first galaxies assembled. Each cluster contains hundreds of thousands of stars bound together gravitationally in a sphere just tens of light years across. From the bulge outward, the galaxy transitions gradually into the disk. No sharp boundary exists. The stellar populations blend together, old stars mixing with younger ones in the inner disk. Only by studying stellar ages and compositions can astronomers distinguish where the bulge terminates and the disk commences. And beyond our galaxy, a neighbor approaches with terrifying inevitability. 2.5 million light-years away, a giant rushes toward us. The Andromeda galaxy, our nearest large neighbor, is heading for collision. The impact is inevitable. The timing is roughly 4.5 billion years from now. The result will reshape both galaxies beyond recognition. Andromeda is massive. Its diameter exceeds ours by nearly a factor of 2. It contains roughly 1 trillion stars compared to our few hundred billion. Its supermassive black hole outweighs ours by tens of millions of solar masses. In almost every measurable way, Andromeda dwarfs the Milky Way. The collision has already commenced, in a sense. The gravitational influence of two galaxies, this massive extends across millions of light-years. Even now, subtle tidal forces are pulling at each galaxy's outer regions. Stars at the edges feel the attraction of the approaching giant. Gas clouds at the periphery experience marginal acceleration toward the collision point. When galaxies collide, stars rarely hit each other. The distances between stars are too vast. Most stars will pass through the opposite galaxy without ever approaching close to another star. But gravitational chaos will reign. Stellar orbits will be disrupted violently. Stars will be flung in random directions, ejected from their original positions. Some stars will be cast out entirely, thrown into intergalactic space with enough velocity to escape both galaxies. These rogue stars will drift alone through the void forever, orphaned by gravitational violence. Other stars will fall toward the merged core, joining a new, larger galactic center that forms from collision. Gas clouds will collide spectacularly. Unlike stars, gas clouds are large and diffuse enough to actually impact each other. When they do, shock waves will compress the gas, triggering enormous bursts of star formation. The merged galaxy will blaze with the light of billions of newly formed stars. This starburst phase will last millions of years before the gas supply depletes. Our solar system's fate during this collision is uncertain. Most likely, our star will be thrown into a new orbit, possibly much farther from the galactic center or much closer. There's a small chance we'll be ejected entirely, cast into intergalactic space, but direct collision with another star remains extraordinarily unlikely. Earth, if it still exists in 4.5 billion years, will have other problems. Our star will be approaching the end of its main sequence lifetime, beginning its transformation into a red giant. The collision's effects on Earth will likely be secondary compared to the dying star's expansion. But the night sky will become unrecognizable. The merged galaxy will no longer be a spiral. Collisions destroy spiral structure, scrambling stars into a more spherical configuration. The result will be an elliptical galaxy, a roughly spherical ball of stars with little internal structure. Spiral arms, the defining feature of both progenitor galaxies, will vanish. Astronomers have already named the merged galaxy. They call it Milkomeda, a combination of both names. This future mega-galaxy will rank among the largest in the local group, potentially even in the local supercluster. It will be a giant dominating its cosmic neighborhood. Other galaxies in the local group will eventually merge with Milkomeda as well. The Triangulum galaxy, the third largest in the local group, will either collide with Andromeda before it reaches us or join the merger afterward. Smaller dwarf galaxies will be consumed one by one. The final result will be a single massive elliptical galaxy containing almost all the local group's mass. This is the fate of most galaxies. In regions of the universe where galaxies cluster densely, mergers happen frequently. The universe's largest galaxies formed through countless mergers over billions of years. Each collision added mass, stars, and gas, building galactic giants. The Milky Way itself has merged with other galaxies in the past. Evidence of ancient collisions hides in stellar orbits and chemical compositions. The galaxy is a construction project billions of years in progress, built from smaller components that crashed together and stuck. And the Milky Way is just one galaxy among many in an even larger structure. The Milky Way doesn't drift through space alone. It belongs to a cluster of roughly 30 galaxies bound together gravitationally. This is the local group, our galactic neighborhood, spanning roughly 10 million light-years across. The local group is dominated by two giants, the Milky Way and Andromeda. These two spiral galaxies contain most of the group's visible mass. Everything else is smaller, often dramatically so. Dwarf galaxies make up the majority of the local group's members, tiny systems containing just millions or billions of stars. The third largest member is the Triangulum galaxy, another spiral with roughly 60 billion stars. It orbits on the outskirts of the local group, possibly bound to Andromeda gravitationally. Its fate is tied to the approaching merger. It will either collide with Andromeda before the Milky Way collision or join the chaos afterward. Most local group galaxies are invisible to the naked eye. Only Andromeda and the two Magellanic Clouds can be observed without telescopes, and those only from dark sites far from city lights. The rest are too small and too distant to perceive without optical aid. They're ghosts in the cosmic darkness. These dwarf galaxies come in different types. Dwarf spheroidals are diffuse clouds of old stars barely held together by gravity. Dwarf irregulars contain younger stellar populations and active star formation. Some dwarfs are so faint they're called ultra-faint dwarfs, containing only thousands of stars total. They're barely more substantial than globular clusters. Why do dwarf galaxies exist at all? They're leftovers from the early universe, small systems that formed when the cosmos was young. Many have been disrupted or consumed by larger galaxies over billions of years. The survivors occupy the outskirts of the local group, far from the gravitational violence near the major galaxies. The Magellanic Clouds are the Milky Way's most prominent satellites. Visible from the southern hemisphere, these irregular galaxies orbit our galaxy at distances of roughly 160,000 and 200,000 light-years. They're close enough that tidal forces are beginning to strip stars from their outer regions. The Magellanic Clouds won't survive independently forever. Gravitational interactions with the Milky Way will eventually tear them apart. Their stars will be absorbed into our galactic halo, adding to the scattered stellar population that surrounds the main disk. This process is already underway. Streams of stars stretch between the clouds and the Milky Way, marking the path of disruption. Other dwarf galaxies orbit the Milky Way as well. The Sagittarius dwarf elliptical galaxy is currently passing through our galactic disk. Its stars are being stripped away with each passage. Within a few more orbits, it will cease to exist as an independent structure. The Milky Way will have consumed another victim. This consumption is normal. Large galaxies grow by eating smaller ones. The Milky Way has merged with dozens of dwarf galaxies throughout its history. Each merger added mass and stars. Chemical signatures in our galaxy's halo preserve evidence of ancient collisions, ghost structures that reveal our violent past. The local group itself is moving. All 30 galaxies share a common motion through space, falling toward a massive concentration of galaxies called the Virgo cluster. This cluster sits roughly 50 million light-years away and contains over 1,000 galaxies. Its gravitational pull affects everything in the local group. Beyond Virgo lies an even larger structure, the Laniakea supercluster. This is a gravitationally bound collection of galaxy clusters spanning 500 million light-years. The local group is a tiny component of this vast assembly, a minor suburb in a cosmic metropolis. From this perspective, even entire galaxies become insignificant. The Milky Way is just one member of a small group, which is itself part of a larger cluster, which belongs to an even larger supercluster. The hierarchy of structure continues upward until you reach the largest known formations in the universe. Here's the paradox that should shatter your mind. You are absurdly, impossibly, incomprehensibly small. A biological organism on a planet barely larger than a dust mote, orbiting a star that's one among hundreds of billions, located in a galaxy that's one among trillions. You could be removed from existence right now, and the universe wouldn't notice. No cosmic balance would shift. No laws of physics would change. Nothing would care. And yet, despite this crushing insignificance, you possess something the universe itself lacks: consciousness, the ability to understand, the capacity to measure, calculate, and comprehend structures vastly larger than yourself. The galaxy is immense, but unaware. You are tiny, but aware. This makes you more remarkable than any galaxy. The galaxy cannot contemplate its own size. The supermassive black hole at the core cannot ponder the mathematics of general relativity. The spiral arms cannot wonder about their formation. But you can. You can look at the vastness of space and understand it. You can calculate distances. You can grasp scales that dwarf you by trillions. The universe has produced very few things capable of understanding itself. You are one of them. This awareness is bizarre. You're a pattern of atoms temporarily organized into a thinking structure. The atoms themselves are ancient, billions of years old, recycled through countless stars. But the pattern they currently form, you, is unique. You will exist for decades, maybe a century. Then, the pattern will dissolve. The atoms will scatter and reorganize into something else. But during your brief existence, you can understand infinity. You can conceptualize distances measured in billions of light years. You can grasp timescales extending billions of years into the past and future. You can comprehend the existence of hundreds of billions of galaxies, each containing hundreds of billions of stars. The fact that you're small doesn't prevent you from understanding the large. This is the strangest thing about consciousness. It's scale independent. Your physical size is irrelevant to your cognitive capacity. You can think about things vastly larger or vastly smaller than yourself. You can visualize atoms. You can visualize superclusters. Your mind operates outside the constraints of physical scale. Humans have only understood our true cosmic position for roughly a century. Before that, we thought we were at the center of everything. We thought the galaxy was the entire universe. We thought stars were tiny lights embedded in a celestial sphere. Every assumption was wrong. But now we know. We've mapped our location, measured our insignificance, and accepted our position as cosmic specks. This knowledge should be depressing. It should make everything feel meaningless. What's the point of human civilization if we're this small? What's the point of individual lives if the galaxy wouldn't notice our disappearance? What's the point of caring about anything when the scales are this extreme? But here's the answer. The point is that we can ask the question. The galaxy can't ask what the point is. Stars can't wonder about meaning. Black holes can't contemplate existence. But you can. That ability, that consciousness, that awareness, it's the most interesting thing happening in this entire corner of the cosmos. We might be alone. Life might be rare. Consciousness might be rarer still. If that's true, then you're not just small. You're also precious. You're one of the few points in space where the universe has become aware of itself. You're a window through which the cosmos views its own structure. You matter because matter has organized itself into a form that can understand mattering. Or maybe we're not alone. Maybe millions of civilizations exist across the galaxy. Maybe consciousness is common. Maybe the universe is teeming with minds contemplating their own insignificance. If that's true, then you're still remarkable. You're still a thinking pattern, still capable of understanding infinity despite your size. The Milky Way is 100,000 light-years across. You are perhaps 6 feet tall. The ratio is incomprehensible. You are smaller than a single atom compared to the galaxy, but you can understand that ratio. You can calculate it, visualize it, and grasp its implications. The galaxy cannot. This is the ultimate perspective. You're infinitesimally small. You're completely insignificant. The galaxy wouldn't notice if Earth vanished tomorrow, and yet you can comprehend the galaxy. You can understand your own insignificance. That understanding makes you significant in a way size never could. So yes, you're small inside the Milky Way, smaller than you can truly grasp. But size isn't everything. Understanding is something. Consciousness is something. Awareness is something. You possess all three. The galaxy possesses none. In that sense, you're not small at all. You're the most complex thing the galaxy has ever produced, the most aware structure it's ever assembled, the first thing it's made that can actually understand what it is. The Milky Way is vast, but you are conscious. And consciousness, however brief and however small, is the only thing that gives the vastness meaning. Without you, without minds like yours, the galaxy would simply exist. It wouldn't matter. It wouldn't mean anything. You're the part that matters. Thank you for joining me on this journey through our cosmic neighborhood. If you enjoyed this exploration of just how small we really are in the grand scheme of our galaxy, make sure to hit that like button and subscribe for more deep dives into the mysteries of space. And don't forget to let me know in the comments where you're watching from. Until next time, keep looking up and questioning everything you think you know about our place in the universe.